All right. Can you hear me? Okay. Um, Welcome. Today we're going to talk about section 15.3. This is independence of path and conservative vector fields. We have already talked about line integrals last time, and before that we talked about fields. Now, one of the most practical applications of line integrals is one that I've alluded to, is that you can calculate the amount of work performed by a field. So if you look at definition 15.3, if you've got some field f in 2 or 3 space, then the work performed by the field on a particle, so it's work by the field is what's doing the work, on some particle along its some path, c, some curve, from some initial point P to Q, is calculated by this integral. Now notice here that we have f dot dr. So what we're doing is we're finding the amount of the field in the direction of the path. So how much of the field is moving in the direction of the curve, and so it's that's what that dot product is calculating there. And then we're adding all of that up. So how much of the field is in the direction of the path? Because work is performed when you have moved a distance, it's a force applied over a distance. So really what we're doing is a small distance there, and then the amount of force in that direction, and we're adding that up over the distance. So this is called a work integral. And it's pretty common, and C here just represents the path of integration, and usually you have to parameterize the path yourself. Usually the path is described by something, and then you have to come up with the path on your own using some parametric equation. So let's look at example 1 here. So we'll flip back to our notes. So we have some field f. It's yx, y in the x direction and x in the y direction, is conservative since the gradient of phi is here. Let's just verify the statement there. They say that the field f is conservative because the gradient of phi is equal to f. So this is going to be the partial of phi with respect to x is just y, and then the partial of phi with respect to y is x, which is f. Okay, so yes, the field is conservative because we found some potential function phi whose gradient is f. Okay, whatever. Now thus, it says the work performed by the field on the particle as it moves from 0, 1 to 1, 1 should be independent of the path chosen. So is that something that I skipped over? I didn't read. Let's see. Note 29. I didn't read it fully. It says we'll see through this next theorem that if a force field is conservative, then the work that the field performs on the particle as it moves from P to Q does not depend on the path. It does not depend on the path. So let's go back to example 1 here. So we have already verified that the field is conservative. So this implies F is conservative. And what that means is that it should be path independent. It doesn't matter how I get from the point 0, 0 to the point 1, 1. The work accomplished by the field should be the same regardless. So let's go ahead and try this in part A here. We want to first parameterize the line from 0, 0 to 1, 1. So this is a line. And the parametric equations that we'll describe r of t for this line, we'll just let x equal t and y equal t, and then t needs to range between 0 and 1. Okay, that parameterizes the segment, the line segment from the origin 0, 0 to the point 1, 1, just like that. Okay, so now let's calculate the line integral. So the work accomplished is the integral over this path C here, and we want f, the field dot dr, And this is going to be equal to the definition here. The conversion is given right there. So f is our function, which was given up here, is y, x. That's the field, the vector field, and phi is xy. That was just to verify that the field is conservative. Okay. Um, what am I struggling with? Um, oh, so what we're going to have to do to break this down further here is use the definition that we learned last time for line integrals. We're going to have to break this up into the two parts. So this is going to be the integral over c of f of xy. This is the x-coordinate function, dx, and then we want the y-coordinate function, so plus the integral over c of the y-coordinate function, which we'll calculate that here is g of x, so this is the y-coordinate function dy. So this is from last time. So these are the component integrals of the work integral. So it's, remember, this is like that projection of the shadow of the surface or the sheet into the xy plane, or the xz plane, or the yz plane. Okay, so that's what we're going to use here to calculate our line integral. So this is going to be the integral over c of the f function here is y, and the g function is x. So we're going to have, let's write that down. So this is y dx, and then plus the integral over our path of x dy. And we've calculated already we've found the parametric equations for each of these. So let's now convert it to the parametric equation from 0 to 1. This is t, y is t, and dx is going to represent dt. And then this is going to be the same integral, dt. So we have 2 times that integral. So let's go ahead and calculate that. So it's going to be equal to 2 times the integral from 0 to 1 of t dt, which is going to be t squared from 0 to 1, which is just 1. Okay, so the work accomplished by the field over that interval from 0 to 1, or from the point 0, 0 to the point 1, 1 is 1. So what we want to do now is find another curve. So let's parameterize another curve here. We'll use r of t. Let's switch colors so to make it a little bit more clear. I'll use green. We'll say r of t. I'm going to parameterize the parabola. I'll let x equal t and y equal t squared. That's x squared. So that's the parabola. T should range between 0 and 1 again. And now the work accomplished is the integral field.dr. And we want, again, to break this up into the two component functions. So this is going to be y dx plus the integral of x dy. And this is going to be, y is t squared, so this is going from 0 to 1 of t squared dt, plus the integral from 0 to 1 of x is t. What is dy, though? So dy is going to be the change of variables. Y is t squared, so we want 2t dt is dy. So let's write that out here. This is dy. Okay. So let's continue. Whoops, wrong color. So this is going to be the integral from 0 to 1 of a total of 3t squared dt, which is going to give me t cubed from 0 to 1, which is 1. So we get the same amount of work, even though we are traveling over a different path to get there. So let's try another one. Let's try along the line y equal x cubed from 0, 0 to 1, 1. First, we have to parameterize the curve again. So this time we'll let x equal t and y equal t cubed. T ranges between 0 and 1. And again, let's just calculate the change of variables here. Y is t cubed. So dx is dt. I didn't do this in the last one, so I'll do it here. Dy is 3t squared dt, just like that. So now, when we set up our integral, the work accomplished, f dot dr is going to be equal to c. We'll use y dx, and then over the curve c, this is x dy. And the y value is t cubed, dt is dx, and this is going from 0 to 1. 0 to 1. X is t, and then dy is 3t squared, dt, 3t squared dt. And now this is going to be the integral from 0 to 1 of 4t cubed dt, which is t to the fourth from 0 to 1. So we're seeing a kind of a pattern here, which is just 1. So regardless, in each path, the work accomplished is 1. And this is all because of this field here. We calculated it at the very start to be conservative. So this is a special type of field who is the gradient of some potential function phi. So the gradient of phi is our field f. And if you can find some potential function whose gradient is the field, that implies that the field is conservative. And it being conservative implies that it is independent of the path chosen. So the work should always be the same regardless of the path chosen. So you might as well choose a path that is easy to integrate along. If it makes your integral easy, then maybe choose that path. If the integral is hard, then maybe choose a different path to integrate along. Okay, well, let's go back to our definitions, and we'll look at the next definition, or the next theorem, I think. Down here, Theorem 1, says the fundamental theorem of line integrals. So it says, suppose you have some field with its component functions f and g, and they say, suppose that it's a conservative vector field, which just means that it's the gradient of some potential function phi down here. So we've got phi as the potential function whose gradient is our field, and some curve that's piecewise smooth, c, and it starts at x0, y0 and ends at x1, y1, and it lies in some region D. So we just need that. It's closed. Some piecewise curve. It doesn't have to be closed. It's just got to be bounded. Okay. Okay, well then what does the theorem say? It says that the work accomplished is the same thing as just evaluating the potential function at the starting point and the ending point. So you just evaluate the potential function at the beginning and the end. So this should look very similar to the fundamental theorem of calculus. If I'm doing the integral of some function from a to b, that's the area underneath the curve. You could do a bunch of Riemann sums, or you could just find the antiderivative of f and evaluate it at the first point and the last point, or the last point and the first point, and take their difference. So that's called the fundamental theorem of calculus. But here we have the fundamental theorem of line integrals, which just says that it's the same thing as evaluating the potential function, the original function. So it's common to write these integrals in conservative fields as its potential function, the gradient of its potential function there, instead of the field, because then it's easier to write the evaluation of that line integral. So in plain terms, let's see what it says here. This means that the value of the line integral of a conservative field along a piecewise curve is independent of the path. It does not matter where you start and end. So in this case, so whenever the field is conservative, I mentioned that you will sometimes just use the potential function, but it's also common to write the line integral in terms of its bounds. So this is the starting point and the ending point of the path, and they don't give a specific curve C because it doesn't matter. You could choose any curve C that you want between those 2 points, as long as it's piecewise smooth, and that's going to evaluate to give you the exact same work. Okay, well I think we can go ahead and try the next example. So let's scroll down here and try example 2. It says confirm that the force field F in example 1 is conservative. We already did that, and then use it to evaluate. Okay, so we didn't evaluate it using the fundamental theorem of line integrals, but let's try that here. So let's just verify it again. So the gradient of phi is the partial of f with a partial of phi. Well, what was phi? Phi was xy, and so partial of phi with respect to x is y, and partial of phi with respect to y is x, which happens to be the original field. This implies that f is conservative. Okay, we already did that. Okay, so now let's calculate the work that we did last time. So this is the work integral, f dot dr, and they said that this is the same thing as evaluating at the potential function at the end, not the beginning, the end, phi of 1, 1, minus phi of 0, 0. So this is going to be phi at 1, 1 is just 1 times 1, and phi at 0 is 0 times 0, and that's just going to be 1, which is what we calculated before. So the work accomplished is 1. Now this is, again, let me emphasize, it's work accomplished by the field. The particle's not doing work as it moves through the field. I mean, perhaps it is, but what we are calculating here is the work accomplished by the field as the particle moves through it. So the particle is moving from the point 0, 0 to the point 1, 1. The field is either helping or working against. Since we have a positive 1 here, that tells me that the field is helping the particle move through that field. Okay. Well, let's look at the next example. They tell us to use the next theorem, so I think that means we have to go read it. So let's go back to the theorem 1532. Oh, there it was. And what the definition, that's definition 1532. It's talking about what it means to be closed. A parametric curve that is represented by a vector valued function r is said to be closed if the initial point r of a and terminal point r of b coincide. So you could have just some path. Let's put some path here, and the starting point and ending point are the same. So here's r of a, and that happens to also be r of b. So r of a and r of b coincide at the same point, and as I move over the field, so I'm moving maybe in this direction, I start at one point and end at the same point, so we call that a closed path. And definition 1533 is what it means to be connected. So if you have a domain D is said to be connected if any 2 points in D can be joined by the same piecewise smooth curve. So let's maybe draw a picture of this. So we're talking about domains or regions here. So this right here would be a connected. This is a connected region. So we're not talking about a path. We're just talking about a region. So this is, we'll call it R. This is connected. And let me highlight it here. So I'll highlight it to show that we're talking about the inside. The inside is a connected region. But now if I were to pinch that to the point that it breaks, something like this, where this is my region R. So this is not connected, so not connected. So let's read the definition again and carefully. It says the domain D is connected if any 2 points in D can be joined by some piecewise smooth curve. So if I choose 2 points inside R here, notice that I can join them with some piecewise curve. But if I choose 2 points in this region R, there's no piecewise smooth curve that can be used to join these two that stays inside the region. So it has to go outside of the region in order to join the 2 points. So this one is not connected. Okay. So let's read Theorem 15.3.2 in order to do the next example. So 15.3.2 says if you've got some component functions f and g that are continuous on some open connected region D, which is what we were just talking about, then the following statements are equivalent. That means that they're all true or all false. So A, what does it say? F is a conservative field in the region D. Okay. And then part B says that the work accomplished is 0 for every piecewise smooth curve in C that's in or on C that is in D. So the field being conservative is the same thing as saying work accomplished is 0 for every piecewise smooth curve that's closed in the region D. Okay, and then what's part C say? The field, the work accomplished is independent of path from the point P to D inside for every point P and Q inside the region D for every piecewise smooth curve. So here, this is the picture. You've got some region, we'll call this D. Let me highlight it. So we'll call this region D. And then we've got a piecewise smooth curve. So piecewise smooth just means that it's smooth on pieces. So this could be my curve C, and maybe I go this way. And now there are sharp corners, but as long as it's piecewise smooth, so every piece is smooth, that's fine. And it's closed. It connects from the beginning to the end. Then the work accomplished over this, as long as the field that this is the overarching field that this is present in, as long as it's in some conservative field, then the work accomplished is 0, that's B, and then the field is that's the same thing as the field being conservative, and then that means it's also independent of the path that we choose. So going from here, I could go around like that, I could go around like this. As long as the curve stays inside the domain D, the region D, and the field is conservative, then it's going to be path independent. So all three of these things are equivalent to each other. So if you know one of them is true, then you know the other two have to also be true. So let's go and use that theorem on this next problem. They say use theorem 15.3.2 to determine whether the vector field is conservative on some open set. Now, you could start hunting out there to find some potential function phi whose gradient is f, but you might be looking for a while in order to find that. Or what we could do is show that it's path independent. But in order to show that, then you'd have to show that it's the work accomplished is 0 on every single path. Or we could just show that let's see, we want that it's independent of path from point P to D. So we can't show it because this is the hard part, for every smooth curve. And so for every piecewise smooth curve here. So that's the troubling part. So we're going to have to find a way around that. So let's see. So how do we want to do this? Well, let's see. So Am I missing something? Let's see, Theorem 15.3.2, that's what we just read. I think I've misnumbered my theorems here. Because you can't show conservative field based on theorem 15.3.2. I think I maybe meant 15.3.3 on that one because I can't seem to show that because these for every statements are hard. This here is hard for every piecewise smooth curve. For every piecewise smooth curve, it's not possible to show for every single piecewise smooth curve because then we'd have to parameterize every curve that we can possibly think of, and we can't do that. So the only other way that we could show that it's conservative is to actually find a potential function. So let's actually come down here and read the next definition and theorem to help us solve this problem. So definition 15.3.4 is the definition of what it means to be simple. A lot of these words what we use in everyday conversation, but so here it says a curve that is simple does not intersect itself between its endpoints, and its region is said to be simply connected if there is no simple closed curve in D that encloses the points that are not in D. A set with one or more holes is said to be multiply connected. So here so that was kind of a confusing definition. So let's see if we can kind of maybe sketch a picture down here. Let's first sketch a simple curve. So this would be simple, closed. It's closed because the start point and end point connect. This curve would be not simple because it intersects itself. So we can draw a little arrow right there. It intersects itself, so it's not simple, and it is closed because it starts and ends in the same location. Now, when we're talking about regions, we're talking about simply connected regions and then multiply connected regions. So this would be we'll say, let's highlight it to show that it's a region. We'll call it D. You could call it R or D. This one is a simply connected region. What is the definition of simply connected? It says that no simple closed curve in D encloses points that are not in D. So it's impossible for me to close a curve in here, put some curve in here that encloses points that are not in D. So no matter what simple closed curve you put inside of the region, it's not possible to enclose points that are not in D. But so what if I have a region that looks something like this? So this is my region. Let's highlight it. Looks like a fidget spinner or something. So this is our region D. And now notice I can come up with a simple closed curve that encloses points that are not in D. So this would be a multiply connected region. So we'll call this multiply connected region. So those are a lot of definitions there. We have simple, closed, we have connected, multiply connected. There's a lot of vocabulary words going on here. We even have open. Open just means that the edges are not considered in the boundary. But let's go ahead and read this next theorem. This one is a theorem that we really like to use. It's called the conservative field test. So as we have seen in this example down here, example 2 or example 3, it's really hard to show that a field's conservative because that means that you have to come out here and find some potential function phi. And that potential function might not be easy to find. You might be searching for a good long while. So there is another way, and it doesn't involve having to check for every piecewise smooth curve because that would take too much time. We want to look at this theorem. It's called the conservative field test. It tests whether or not a field is conservative. You have two component functions, f and g, and they have to have continuous first order partial derivatives. So that means partial with respect to x and y. On some open region D, that's talking about something like this. Open means that it doesn't have to include the boundary. And if the vector field f is conservative, then the partials have to be equal. The first partials of our component functions have to be equal over the region at every single point in the region. They also say conversely, if D is simply connected, like the region in blue there, then the partials have to be equal. First partials have to be equal in D. Then the field is conservative. So that means that it goes both ways. So we know that if the partials are equal, then the field's conservative. If the field's conservative, then the partials have to be equal. So it goes back and forth. It's an if and only if is really what we're getting at there. So now let's go and solve this one. So this is our function lowercase f, and this is our function lowercase g. And so by the conservative field test, what we want is the partial of f with respect to x. So that's going, a partial of f with respect to y. You want the x component function with respect to the other variable is going to be 1. And then we'll check the y component function, which is g, with respect to x, which is going to be -1. Determine whether the field is conservative. And here we see that the partials are not equal. So we have that the partial of f with respect to y is equal to 1 is not equal to -1, which is the partial of g with respect to x. So remember, that's an if and only if. So if by the conservative field test, this implies that the field f is not conservative. That means that it's not path independent if I were to integrate over this field. So there could be some point in some path that gives me a different value at some other point when I'm integrating over this field. Okay, well, let's try another example. Example 4 says let f be this field. Show that f is a conservative vector field in an entire xy plane. So let's take the partial that we'll have to label our component functions. This is f, and we'll label this one with g. Now, the reason I'm labeling the component functions here is because they didn't label them. So if I start talking about f, lowercase f and g, then it's going to be confusing. What is f and what is g? So I'm labeling them here so that we know that the partial of f with respect to y is going to be 6xy. And now let's find the partial of g with respect to x is equal to whoops, I missed a squared on my y. So this is going to be partial of g with respect to x is 6 times x times y squared. So these two are equal. So then we can say by the conservative field test, f is conservative. And notice that this equality does not depend on values of x and y. So what that means is it's conservative on the entire xy plane. No matter what I choose for x and no matter what I choose for y, these two are going to be equal. So if I choose x to be 0, then they're equal. If I choose x to be 10, they're going to still be equal regardless. Okay, so for part B, it says find phi by first integrating the partial of phi with respect to x and then the partial of phi with respect to y. So here, so there must be some potential function phi out there. This is the potential function. Potential function. And so we don't know what it is. It's out there. We know it has to exist because the field's conservative. And we know that its gradient is going to be f. Well, we know what f is. F, let's go back and look at it. F is up here. It's 2xy cubed. And then y is 1 plus 3x squared y squared. And so now this phi must be so this, let me maybe rewrite this. F, the field, this x component is the partial of phi with respect to x, and this is the partial of phi with respect to y, because it's the gradient of phi. So let's write both of those down. So I'll do one of them in blue and the other in green. So the partial of phi with respect to x is equal to 2xy cubed, and then the partial of phi with respect to y is equal to 1 plus 3x squared y squared. So here we can do the antiderivative. This is partial integration is what we're doing. So we're going to do the antiderivative of phi with respect to x here. So this is going to be the, and we're doing it indefinitely, so it's a partial antiderivative. So 2xy cubed dx. So what that means is I'm going to get x squared y cubed, but plus, instead of a constant, I'm going to pick up some function of y, h of y. So this would have disappeared in the partial derivative, so I'll just say function of y. Okay, well now let's do the antiderivative here with respect to y. So that's going to be 1 plus 3x squared y squared. And we'll do the antiderivative with respect to y. That means I'm going to get x squared y cubed plus y plus, we'll use some other letter. Let's see, f and g are used, h. Let's use another letter, maybe k, k of x. So now here I've got another function k of x. So here, if I take the partial of one of these with respect to the other variable, then these partial functions are going to disappear. So let's take the partial derivative of this function with respect to x, say. So then we get this is, we're looking at phi here. So this is phi, and this is phi. So we can basically compare these two to recognize what we're getting, what we're close to. So by taking the partial of phi in blue up there with respect to the other variable, we already know what it is with respect to x. Let's do it with respect to y. We're going to get 3x squared y squared plus h prime of y. Well, if you compare this to this function, the partial of phi with respect to y, that's going to imply that h prime, let's use blue still, that's going to imply that h prime of y is 1, which implies that h of y is equal to 1 plus some constant c. So now we can finally put together phi. So what is phi? Phi of xy is equal to, let's go back up in blue here. Right here it is. X squared y cubed plus h of y, we just found out is, oops, I didn't do the antiderivative. That's a y. Plus y plus a constant. So this is phi. So we were able to find that potential function, and you can choose any constant c that you want. So now, in the next example, we can actually evaluate using our potential function. So let's evaluate this phi at the upper bound and phi at the lower bound. So our potential function, let's write it down here. It was x squared y cubed plus y. And it doesn't matter what constant it is, so I'll just choose constant to be 0. So then this is going to be equal to 3 squared times 1 cubed plus 1 squared times 4 cubed, which ends up being 9 plus 64. Is that right? Oops, I put a plus in between these. We want a minus, so 9 minus 64, which is negative, negative 56. Is negative 55? What is this? Ooh, I evaluated this wrong. I'm sorry. Let's fix this. So I want phi at the upper bound, so that's, I forgot the y value, plus 1 minus phi at the lower bound, which is 1 squared times 4 cubed plus 4. There we go. I knew I was making a mistake. So that's 10 minus, that's 64, 68. So that's negative 58. There we go. So that's the evaluation. Okay, I've got to pause the video, but I'll start back here in a minute. Okay, I'm back. Let's go ahead and continue here. So they say find, let f equal e to the y I plus x e to the yj to note the force field in the xy plane. And then A says verify that the field's conservative in the entire xy plane. We've done that before. So I'm going to call this f of xy and this g of xy. And so now we want the partial of f with respect to y is e to the y. And this happens to equal the partial of g with respect to x, which is just e to the y. All right, so it's conservative. So maybe we should go through the process of saying conservative y by conservative field test. Okay, so you could abbreviate CFT or something like that, but it is important that you state why it's conservative. You can't just show this and then expect your reader to know. So on a test or a quiz, definitely use the conservative field test. So it's conservative. Now for part B, they say find the work done by F on the particle that moves along the semicircular radius in this direction. So F is moving, F is the blue field here, and then in red is the path. Well, now we've shown that it's path independent, it's conservative. So we can just integrate along this line. We don't have to use the fact that it's a there's a few different things that we could do here. We could just integrate along that line. That's one way to do it. The other way to do it is to find the potential function phi. I think we'll go ahead and do that. So the gradient of phi is equal to e to the y x e to the y. So then let's do the antiderivative of e to the y with respect to x. That's x e to the y plus some h of x. And now let's take the partial of that with respect to y. So the partial of phi with respect to y, this is phi. So let's take the partial of that with respect to y. That's just going to be x e to the y plus nothing. Because the partial of that with respect of, whoops, this is not nothing. This should be y, some function of y. And so its partial derivative is just going to be h prime of y. And we want to compare that to this. And this implies that h prime of y is 0, which just implies that h prime of y is just a constant. So now we have phi. Phi is nothing more than just x e to the y. And so if we want to calculate the work done by the field here over this path, we can choose whatever path we want. In this case, I'm just going to say phi at the point 1, 0 minus phi at the point -1, 0. So this is going to be x is 1 times e to the 0 minus x times e to the 0. So this is 1 minus -1 or 2. So no matter how you evaluated the path here, you should get a 2 along this path. I'm looking down at my notes here and I see that I got a -2. How did that happen? It's because I evaluated at the starting point first and then the ending point. So I've got these switched. Oops. So let's fix that real quick. So this should be -1, 0, and then 1, 0. We want the ending point and then the starting point. So -1, 1, so it should be -2 there. All right, well, that's the end of this lesson. Hopefully I can teach this to you guys in person. If not, then hopefully you can watch this video as well. I will see you guys next week.